Hi, good day everyone. Today we are going to be continuing our signals and systems review, but in particular we're going to be looking at with respect to discrete time and discrete convolution, which forms the basis of what we're looking at when we start off with discrete signal processing. So this lecture will basically do the review of the properties of the unit impulse, and then we'll watch at the shifting, the sifting, and the connection to the unit step properties. We'll also look at system properties, impulse response, and then we'll move on to discrete convolution. So the unit impulse here is basically where we have an instance in time and where we have an instantaneous value in particular. So the unit impulse, the unit part of it means that it's a magnitude 1, and because of the impulse it occurs only at this particular time. Because we're dealing with discrete time, this basically is going to represent as delta of n, and n here represents the 0 value. If we decide to shift it or delay it accordingly, remember because n here is positive, if we say we want to shift it to the right, this is actually going to be a delay, so that should be n minus k. In this example here, we shifted it, or we delayed the signal by 3 units. So this is why we get n minus 3 here in the brackets. So one thing to note is that our unit impulse in discretized time is the first difference of a unit step. Meaning that, as of such, if we take the unit step and then we delay it by 1, and we subtract these two, we will get back our unit impulse accordingly. Alternatively, if we do a summation of unit impulses, we can also get the unit step. But the property of the unit step is such that for n equals 0, everything is 0, and for n equals 0 and n more than 0, it's going to be 1. So as of such, this summation series here that we're observing, for it to satisfy the unit step condition, m here must be equal to 0 and goes towards infinity in order to get our unit step. Now, using the unit impulses, or a series of unit impulses, this gives us the idea of how we can sift or extract values from any arbitrary discrete time signal. And the reason for this being is that if we have an arbitrary discrete time signal known as x of n, and we multiply this by the unit impulse, delta of n, we basically sift out the property at n equals 0, because there's no delays affected by either one of these signals. However, if we want to extract out a k index value, where k could be like 1, 2, 3, or minus 1, minus 2, minus 3, and so forth, we need to shift the unit impulse accordingly in order to do this extraction. So this is where we use this shifting property of the unit impulse, where it's delta n minus k, and we multiply by an arbitrary signal to get that instantaneous value at that k index. Now the definition above basically says multiplying any sequence by unit impulse selects or sifts out the value of the sample at the instant of the impulse. But basically, if we switch sequence here and sample with signal, this is actually what gives us our sampling property, or the sifting property of the unit impulse. So in particular, and to visualize this, we're given our arbitrary signal here, x of n, which is basically going to be a series of stem plots of the instantaneous value, because remember, x of n here is going to be a discretized time signal. If you wanted to extract out x of minus 2 here accordingly, we need to shift the unit impulse to the left, meaning that we need to make sure that the signal is advanced by 2 steps. So this is how we get delta of n plus 2. And then we multiply this by x of minus 2 here in order to sift out this value. Similarly, for the minus 1 value, we do the same thing. So we have x of minus 1, but delta is going to be n plus 1. The 0th value is x of 0 and delta of n. The 1 value will be x of 1 and n minus 1. The 2 value here is going to be x of 2 and n minus 2 here accordingly. The summation series here that we observe gives us if we decide to extract out more than one value, and the limits here would be from k equal to the lower limit to the uppermost limit in order to get this extraction of values. This equation here should look very familiar to anyone who did continuous time signals and systems. And basically this is the discretized form of a convolution type summation. So the unit step function here is given as u of n, where for everything n less than 0 it's 0, and everything for n greater than or equal to 0 it's going to be 1. The unit impulse function is that at that instantaneous value of discretized time, meaning that n equals 0, it's going to be 1. But for everywhere else, where n is not equal to 0, it's going to be 0. Integration and differentiation in particular, in discretized time, follows different sorts of rules than from continuous time. So for integration property, we basically just use a summation series to represent our integration. And differentiation is basically the difference between two consecutive samples. For periodic signals, what we can observe here is that if we had it in continuous time with respect to t, for discretized time we just replace all the t's here with n's accordingly, and we pay attention to the casing. So for common t here it will be common n, and for capital T here it will be capital N. As we can see here for the finite energy signals, continuous time we had this integration property here. It's now going to be replaced by a summation property here for discretized time. Delta of x, modulus of x of t all squared, the modulus still transfers over, but the t here just switches to n. The dt here represents this for continuous time, but for discretized times we don't have a dn because we have the summation series here accordingly. The limits, however, remain the same for where we're actually trying to prove that this energy signal exists for. Similarly, if you watch for the finite power series here, this limit as t tends towards infinity now becomes the limit as n tends towards infinity. Keeping in mind this is capital T here and capital N here. 1 on 2t becomes 1 on 2n. The integration between t and minus t becomes a summation series in between negative capital N and positive capital N. For common n, common t here is replaced with common n. The dt here is already accommodated for the summation series, and the limit here remains the same. We will be looking at finite power signals in particular when we decide to do spectrum analysis later on in this series. Now, any discretized time system basically transforms any input sequence to output sequence using some sort of transform or some sort of software processing and so forth. We can do this sample by sample, being that this will be done sequentially. So each sample is processed one at a time, and this is essential like how serial communication works. In particular, you want to use serial processing or sample by sample processing for any real-time system because we're dependent on the signal coming in a sequential manner. And as it comes in a sequential manner, each sample needs to be processed accordingly. However, if we're dealing with non-real-time systems or we already have the data pre-configured, we actually can do this using a matrix operation instead. So this works for where we have data already existing or where the data is stored, and this is referred to as block processing. Block processing is also the first indicator of parallel processing that can be done. And this actually is basically a matrix operation. So in this case, our H operation here, as we saw above, is represented by this matrix here. And the H basically represents a transform that transforms the input sequence to the required output sequence. The input sequence here being the X vector. Now the linearity property that we observe here is basically once we have any sort of required transform affecting each one of the samples accordingly, this transform can be extracted out accordingly for everything as of such. So in this case, because we had the a1 being a function of a1 x of n and then a function of an x of n and so forth, the a1 and the an's are not technically being manipulated by this x of n. They are constant, so they can be extracted out accordingly, and then we just focus on the function that applies to the x signal itself. For time invariance, the mathematical notation basically means that once we have a y signal being the outputs and an x signal being the inputs, any delays that affect the y signal should also directly affect the x signal accordingly and have a direct one-to-one mapping. If this mapping cannot be proven or cannot be achieved in some way, we do not have a time invariant signal, we have a time variant signal. The causality property basically means for a system or signal to be causal, it only exists for n greater than or equal to 0. If for some instance the signal exists for n less than 0, the signal is referred to as an anti-causal signal. So for any discretized time signal, because we're going to be dealing with causal signals for this course in particular, that means that the k-index here for a summation series must always start at 0, or it must always be positive, and that we go towards some positive finite value for a summation. And in particular, we'll discuss this in a lot more detail when we actually hit the sampling lecture. So the impulse response here that we observe is basically for any linear time invariant system, you can use an impulse response to characterize this system in particular. If we use our sifting property here accordingly, and we try to extract out the x of n signal for any impulse response, basically what happens here is that instead of x of k being multiplied by delta of n minus k, we do this such that delta of n minus k here is replaced by h of n minus k. H of n here being the original h of n signal, and then we delay this accordingly by h of n minus k. So because we now map delta of n minus k to h of n minus k, that means we now get x of k, h of n minus k here, for a sifting property. And as of such, what this means is that if we want to get our output sequence here, using an input sequence x of k, and our system equation here being h of n that was originally included, but now it's going to be delayed of h of n minus k, we can apply the sifting property here for our input sequence and our system here to achieve our y of n. And this maps back to where we were discussing how an input signal or input discrete time signal can be manipulated by a system h accordingly in order to produce our output discrete time signal y of n. Alternatively, we can make this into a double summation series where we have our summation here for n and k accordingly, where in particular we'll be using the yellow highlighted block to represent our system here. The shorthand version to represent this will be y of n is equal to x of n star h of n, and the proof that we just now observed here for this is what we refer to as the convolution sum or discrete time convolution. The order of the convolution, as you can see here mathematically, it means that it does not matter. We can decide to hold the x of n signal constant and shift the h of n signal accordingly by h of n minus k, or we can hold the h of n signal constant and we can shift the x signal accordingly by x of n minus k. So it doesn't matter the order of the convolution, you will still get the same output regardless. There's one thing to note in particular. During the convolution, let's say the h of n signal doesn't converge, meaning that there's no n towards it, the output response is what we're going to refer to as an infinite impulse response. But however, if the h of n signal does converge, or it does n at a finite value, refers to the output sequence is going to be referred to as a finite impulse response. And when we get towards filter design in particular, we'll be looking at these infinite impulse responses and finite impulse responses with regards to these filters and how we design for them accordingly. So let's watch how we can actually apply the convolution equation here in particular towards any sort of causal sequence that we may apply regards to this equation. So if we wanted to extract out y of naught, meaning that we substitute n equals to 0 here, or k equals 0 here, sorry, we substitute k equals 0 here in order to get this. Nope, sorry, we substitute n equals 0. The question here that we're going to ask here is what happens when h of minus k here, what do we get this value as? And this is basically if we take h of k here and we just reverse the signal accordingly. So continuing the expansion here as we go along for y of naught, we'll end up getting y of naught is equal to x naught h naught plus x1 h of minus 1 plus x2 h of minus 2, and we can keep on going as of such. If we try to solve for y of 1 here accordingly, now because we have h of 1 minus k, this is actually where we have a slide accordingly in the signal. So this is if we flip the signal using h of minus k and then we shift it to the right once because of this 1 property. So as of such, y of 1 here, if we start doing the math fits, it ends up going such that it will be y of 1 is equal to x naught h1, x1 h naught, x2 h of minus 1, and so forth as we keep on going. Eventually we can do the same thing to solve for y of 2, y of 3, y of 4, and y of 5. Now actually let's observe this if we decide to use two input sequences that are already predefined. So in this case we're going to be using the x of n signal here and the h of n signal here. Now it's important at this point that you actually do copy the signals and attempt this on your own, even though I'm going to show you how this can be done regards to doing the actual working and so forth for this. So because we're dealing with x of n and h of n, the first thing that we need to do is to flip the h of n signal accordingly, because now we're going to be dealing with respect to x of k and h of k. So instead of x of k here being 1, 3, 4 and h of k is going to be 5, 4, 2, because we flipped the h of k signal to h of minus k, it's now going to be 2, 4, 5. We then arrange this accordingly into what we refer to as a convolution table here. We watch where, in this case, where the signal starts to overlap for each one of these outputs that we're trying to calculate for. So because we have an overlap here in particular, this will be the first instance where you have y of naught. In this particular case, we have no overlaps for the -1 index and the -2 index here accordingly. So these values here for x of k don't exist, so they can just basically be 0. So in solving for y of naught, all we care about is where the overlap occurs. So we just multiply the two values there accordingly, and as of such, because it's 1 and 5, we just end up getting 5. We then shift the x of minus k signal once to the right. In this case, this would be where we had our h of 1 minus k. We do the same thing as we did before, where we observe where the overlap occurs. For anything that there's no overlap, it's basically that the blank spaces are going to be 0 accordingly. So wherever the overlap occurs, we multiply those two signals, but because we have two overlaps here, it's going to be 1 multiplied by 4 plus 3 multiplied by 5, as you can see here for the y of 1 equation. So our end result here is going to be 19. We then shift the h of 1 minus k signal once again to the right. So now in this case it's going to be h of 2 minus k. And we just keep on repeating the steps accordingly in order to get for y of 2, y of 3, y of 4, and y of 5 accordingly, and we can keep on going. So what ends up with regards to this convolution table is that this is what it will end up looking like. And we can see basically that the overlap ends at this point. And for each one of these overlaps, there's going to be a y of 0, or y of 1, y of 2, 3, 4, and 5 accordingly. And we end up getting our output sequence here being the output of the convolution equation. And this output sequence here is represented as basically a series of values because you're dealing with discrete time signals. Now this method works, but as you can see, we only had the input sequence here being only 3 values each. And this ends up taking a lot of lines to work out if we're doing this by hand in order to get to our y of n value. So there has to be a more efficient or compressed method in order to save time and to save space when actually applying this to any convolution problem. So if we decide to watch another approach in particular, we had y of 0, y of 1, y of 2, and so forth. And we know basically because we're dealing with causal signals or causal systems, h of any negative in the x is just going to be 0 regardless. What happens here is that the y of 0 system is going to be x0 h0, y of 1 is x0 h1, x1 h0, and so forth for y of 2 and so forth. If we put this into a different table in particular, what we can see here is that we can arrange this table accordingly, where we have all of x0, x1, x2, x3, x4, and so forth could be here on the topmost row of the table, and h0 to h3 can be on the leftmost column of the table. Now note, because we're using this table in particular, we didn't need to flip the h signal. We actually could keep the sequence of the h signal here accordingly, and we could still produce this as well. This table is actually the convolution table you want to use when you're actually doing any sort of convolution. So one thing to note, wherever a cell has some sort of overlap, this is actually going to be a multiplication. So in this case, the h0 and the x0 cells overlap here. So there's h0 by x0. Here is going to be h1 by x0. Here will be h2 by x0, and so forth. So after we put in our x signal here, because our x signal here is 134, and our h signal here was 542. We then multiply accordingly to get each one of these. So 1 by 5 will give us 5, 5 by 3 is 15, 4 by 5 will give us 20, and so forth. After we fill off the table, we then sum across the anti-diagonals in order to get our output sequence. So as of such, when we solve for y0, the anti-diagonal here is going to be just 5. For y1, it's going to be 4 here, and then 15, and we add these two, so we get 19. For y2, it's 2, 12, and 20, so we get 34. y3, it's going to be 6 and 16, so we get 22. And y4 here, it's going to be 8. So we get the same output sequence as from before. If we decide to plot these sequences accordingly, this is actually what it will look like. So these are actually just the graphical representation of the results. So now actually that we've seen how we can actually use the convolution table to solve for a convolution, it's time for you to actually attempt a problem regards to this. So given the example problem here, I want you to actually pause the video and attempt to solve for this and to produce the output sequence y of n as a convolution of x of n and h of n. You're given the properties here for t and n, so that way you get able to get the input sequences accordingly. So pause the video at this point, take some time to attempt the problem, and then unpause it after you make your attempts to actually see what the solution is going to look like. Alright, so hopefully you actually did attempt the problem. So we're now going to observe what the solution looks like for actually when you're doing this problem. So for the first step we do is that we basically find out what is going to be our input sequences here, being x of nt and h of nt. X of nt here was equal to exponent of minus n of t here. We were given the value for capital T, meaning 0.1 seconds, so we just substitute that as 0.1, and n here goes from 0 to 3. So we just substitute n equals 0, n equal 1, n equal 2, n equal 3 in this part here accordingly, and we get our input sequence here accordingly for x of n. H of n we do the same thing as before, as we did for x of n. T here is being 0.1, and then we substitute n0, n1, n2, n3 accordingly to get our h of n sequence. So after we do this, we will get our x of n sequence here and our h of n sequence here accordingly. We then put this into the convolution table that we just now saw before in the previous slides. So in this case, our x of n sequence here is going to be on the topmost row. So 1 here, 0.9 here, 0.8 here, 0.7 here. And our h of n sequence here is going to be on the leftmost column. So 0 maps here accordingly, 0.1 here maps, 0.2 here maps, and 0.3 here maps. We then fill in the values for each of these cells, watching where the overlap occurs. So 0 by 1 here is going to be 0, 0 by 0.9 is 0, so this entire row here goes 0. Then we have 0.1 by 1, we have 0.1, 0.1 by 0.9048 will give us a value here, and so forth. So the completed table will look like this. We then sum across the anti-diagonals to get our y of n signal. So in this case, we have 1, 2, 3, 4, 5, 6, 7 anti-diagonals. So we're expecting 7 values for y of n. And after we sum across here accordingly for each one of these, our y of n sequence will end up being this value here. Now, for anyone who is actually trying to attempt to do this and wants a quick way to actually observe the value, if you use a MATLAB or Octave, you can actually use this example code here on this slide in order to achieve the n value. And you can actually see what it looks like in order to verify that you did do your answer correctly. The subplot commands here basically would just give us the graphical results as we just now saw from the previous examples. So the take home from this lecture in particular is actually how do we do discrete time convolution. And the method that you want to use is using the convolution table as you saw in the second example that we saw. So you want to use that convolution table because you don't need to flip the x of n signal. You can just put the x of n signal on the topmost row and the h of n signal on the leftmost column. Then do the multiplications accordingly and just sum across the anti-diagonals in order to get to the y of n signal. So that brings us to the end of our review for the signals and systems regards to course. The next lecture will actually start on the basics of discrete signal processing and where we actually move forward regards to this course. So see you then. Bye.